Thank you for introduction. My name is Kaoru Mizuta from Riken RQC. So today I'd like to talk about our recent study on optimal time periodic Hamiltonian simulation. This is the outline of my talk. So briefly reviewing on Hamiltonian simulation algorithms on quantum computers, respectively for time independent and time dependent cases, I would like to discuss about our Hamiltonian simulation protocol for time periodic cases. So let me start the introduction. Hamiltonian simulation is to implement time evolution operators of quantum many-body systems here on quantum computers. So once we can realize time evolution operators on quantum circuits, so we can simulate quantum many-body dynamics, or namely, so we can solve the Schrödinger equation. And by using a subroutine in quantum phase estimation algorithms, we can accurately obtain energy eigenvalues or energy eigenstates. So if we allow the time dependency, we can also simulate adiabatic quantum dynamics. So their application widely covers quantum chemistry and condensed matter physics. Maybe the most important problem in this field is whether how we can organize the time evolution operator UT from a given set of elementary gates. Here, so there are two important elements. The first one is accuracy. So we would like to make the error arbitrarily small. We denote it by epsilon. And we also, the second important factor is the efficiency. So we would like to realize time evolution operator with as few resources as possible, both in time t and the error epsilon. One of the most simplest and well-known protocol for the Hamiltonian simulation is so-called throttlization technique, so which is both applicable for time-independent and time-dependent cases. So this is the Lee-Suzuki-Trotter formula for the two local Hamiltonians. So here, so we organize the time evolution operator for the right-hand side. So here is a quantum circuit composed of two layers of two-qubit quantum gates. Although so its structure is quite simple, so it requires a gate complexity polynomially increasing in the desirable accuracy 1 over epsilon. So when we want to consider large-scale quantum materials in the future, so throttlization may be unsuitable. Recently, some alternative methods have been developed. Here, I would like to briefly review on qubitization technique for time-independent Hamiltonians and truncated Dyson series algorithm for time-dependent Hamiltonians. So let us begin with time-independent cases. So qubitization techniques, or equivalent quantum singular value transformation, allow to apply a polynomial function of Hermitian matrices by exploiting the block encoding and quantum signal processing. In the case of a Hamiltonian simulation, we apply the polynomial approximation of the exponential function of the Hamiltonian H. In order to execute this procedure by the qubitization techniques, so we need some computation resources. First, we need ancillary qubits, which is required for the block encoding. So this is typically proportional to the logarithm of the system size n. The second one, the complexity is the most important factor. So this is a complexity measured by the number of block encoding of the Hamiltonian here. And in fact, it determines the computation time. In the case of qubitization techniques, so query complexity has two terms. The first one is a linear increase in time t, and the second term is logarithmic increase in 1 over epsilon. So this is known to be optimal scaling, both in time t and the accuracy epsilon. Second, let us consider the time-dependent cases. So in this case, the difficulty is coming from the formula for the time evolution operators. So in contrast to time-independent cases, it is not a univariate function of the Hermitian matrix, and it includes time-ordered operation and integration. So compared to time-independent cases, it is difficult to execute the Hamiltonian simulation. Recently, so truncated Dyson series algorithms resolved this problem by introducing the time discretization. So they introduce some ancillary qubits, which leverage the discrete time, and they execute a Hamiltonian simulation in a similar way to the truncated Taylor series algorithms. In the algorithms, so they also use ancillary qubits and query complexity. Here, so in addition to the NA here, which is required to block encoding, so we need some ancillary qubits, which mainly used for labeling the discretized time. The query complexity is given by this product here, so linear increase in time t and logarithmic increase in t over epsilon. When comparing these algorithms, so we can see some gap between these two algorithms. For time-independent cases, so this the query complexity is optimal both in time t and 1 over epsilon, and moreover, so their contributions appears in an additive way. So this is the theoretically best scaling for the Hamiltonian simulation. On the other hand, so while the truncated Dyson series algorithm achieves optimal or nearly optimal scaling in both in time t and 1 over epsilon, however, so this is productive. So there is a large gap between these two algorithms, and this comes from the difficulty of handling time dependency. So our question is that, can we achieve the best cost like this additive form for simulating time-dependent Hamiltonians? So this leads to our results on time-periodic cases. So let me discuss our results. So our focus is time-periodic Hamiltonians. So we consider time-dependent Hamiltonians which have a time periodicity. Here, capital T denotes a period. So this is equivalent to that the time-dependent Hamiltonian is well described by the Fourier series expansion. Here, Hm denotes the Fourier component Hamiltonian, and the omega, so which is the inverse of the period. And here we assume that the frequency is size independent. We also assume that the cutoff M max is order of 1. So why should we focus on the time periodic Hamiltonians? The first reason is the relation. So the time periodic Hamiltonians just lie between the time independent Hamiltonian and generic time dependent Hamiltonians. So this is a significant class of time dependent Hamiltonians. The second reason is the versatility. So time non-equilibrium quantum many-body systems driven by time periodic Hamiltonians are well known as Floquet systems, and they have been vigorously studied in the context of quantum chemistry and quantum matter physics. For example, they include laser irradiated materials. So, and we also assume allow the time dependency. So the time periodic Hamiltonians can be also applied to adiabatic state preparation. So we summarize our results. So we have developed the Hamiltonian simulation algorithm for time periodic cases. In our algorithms, so we use the block encoding for each Fourier component Hamiltonian Hm as an oracle. Here, so the block encoding is denoted by OM, so which is a unitary gate whose whose diagonal block elements give the Fourier component Hamiltonian. Our results show that so time periodic Hamiltonian can be simulated almost as efficiently as time independent cases, despite the existence of time dependency. Here, so I briefly outlined our algorithms. The idea is to avoid the usage of Dyson series expansion. So instead of the Dyson series expansion, we use this formula derived by the Floquet theory. The left-hand side means the dynamics and the time periodic Hamiltonians. In the right-hand side, this ancillary systems label the Fourier index L, and so on quantum computers, we prepare some ancillary qubits for Fourier index. Second, so this is a remarkable point. So we can calculate the dynamics under time periodic Hamiltonian by the time-independent Hamiltonian simulation. Here, effective Hamiltonian H effective involves the Fourier index L and the Fourier component Hamiltonian H0 and Hm. Finally, we make a measurement on Fourier indices here, so that the state is projected to this superposition. So since we can compute the dynamics under time periodic Hamiltonian by time-independent Hamiltonian simulations, we can expect that time periodic Hamiltonians can be simulated as efficiently as time-independent cases. However, so this strategy is not so simple because this formula involves the infinite dimensionality. So although the left-hand side is finite dimensional dynamics under time-dependent Hamiltonians, right? The right-hand side can get rid of time dependency. However, so this involves the infinite dimensionality because the Fourier index L runs over all the integers. So we cannot directly simulate the right-hand side on quantum computers. So in order to complete our algorithms, so we should resolve the infinite dimensionality. So here, so in order to resolve this, we show the list of what we did for the algorithms. So first, we introduce some proper intertruncation for the Fourier indices Lmax, and we also introduce a new truncated effective Hamiltonian for cubitization technique. Finally, so due to the infinite dimensionality, so the success probability of post-selection is quite small. So we should amplify it up to 1. So we also developed a new amplitude amplification protocol exploiting the symmetry of time-periodic Hamiltonians to enhance it. Due to the restriction of time, we concentrated on the first step here. In the first step, we introduced some cutoff Lmax for the Fourier indices. However, so when we introduce a cutoff, there appears some approximation. So how large cutoff Lmax is required to achieve error epsilon. So in order to derive proper cutoff, we use a discussion based on the Lieb-Robinson bound. According to the Flock theory, so Fourier index L can be recognized as the lattice point L, and the Fourier component Hamiltonian HM can be recognized as hopping by the site M here, like here. And these matrix elements appearing here can be seen as a transition rate from the site 0 to the site L here. So by using this mapping, we can use the discussion in similar to the Lieb-Robinson bound on one-dimensional finite range systems. By using this technique, we obtain the explicit formula for the cutoff Lmax in this form. Actually, so this form of cutoff appears an additional term of query complexity, and it also determines the number of ancillary qubits by its logarithms. So we summarize our result, our cost for the algorithms. So we show the query complexity for simulating time-periodic Hamiltonians. We obtain two results based on depending on the time scale. The first case is where the time t is as large as the period t, and the second case is where the time t is relatively larger than period t. We obtain these two results here, so this is rather complicated. But here, so alpha is an energy scale of the Hamiltonian, which is polynomial in the system size n, and we note that the frequency omega is much smaller than the alpha. So we can summarize these forms in this way. So the additive form of a linear increase in t and the logarithmic increase in 1 over epsilon. In the second case, we have additional factor omega t. However, so this is quite small due to this assumption. So when we see this scaling, respectively for time t and accuracy epsilon, so this is optimal scaling. So in time t, and this is nearly optimal scaling in 1 over epsilon. Let us compare these results with the previous algorithms for time-independent and time-dependent cases. So as you can see, so the above two cases, including time-periodic cases, share the query complexity with the time-independent cases. So we can say that the time-periodic Hamiltonians can be simulated as efficiently as time-independent cases. The second case has an additional factor omega t. However, so this is quite smaller, much smaller than the time-dependent cases, since the truncated Dyson series algorithms have a completely productive scaling. So we can say that so time-periodic Hamiltonian simulation can achieve efficient additive query complexity like cubitization technique. So we can also compare the number of ancillary qubits. So this is our result here. Actually, so here NA is the number of ancillary qubits required for block encoding. So this we have some additional terms here. Actually, this is mainly used for labeling the Fourier indices here, and this is much smaller than the label for discrete at time used for truncated Dyson series algorithms. So this concludes that we can save the number of ancillary qubits by accurately describe the time-dependent dynamics by using the Fourier indices. Finally, so we summarize our results. So we show that the time-periodic Hamiltonian can be simulated almost as efficiently as time-independent cases, so despite the existence of time dependency. We also show some perspectives. So since time-periodic Hamiltonians have been vigorously studied in condensed matter physics and quantum chemistry. So for example, we can consider some various applications toward in this field. And we can also expect that this algorithm can accelerate the adiabatic state preparation algorithms. We also note that we are also interested in the generalization of algorithms. Actually, our efficient query complexity relies on the existence of Lipp-Robinson bound. In the case of time-periodic Hamiltonians, we use a one-dimensional finite range system. It can be mapped to one-dimensional finite range systems. By considering other systems, we also expect the extension. For example, we can also consider time-periodic Hamiltonians with exponentially decaying Fourier components like this form. And we can also consider periodic time-dependent Hamiltonians where the frequency is designated by an n-dimensional vector. In these cases, we can also obtain additive query complexity like these forms. So we are interested in how large class of time-dependent Hamiltonians can be efficiently simulated in a similar manner. So this is the end of my talk. Thank you for listening.
Okay, thank you for this nice talk. Any questions?
Thank you for the. Okay, thank you for the nice talk. So, but naively, if you wanna get time periodic system is just like repeating the same things many times. So in that sense, if you very accurately simulate one step, then or if you just figure out the Hamiltonian that represents that one step unitary, it's almost like.
Yes, actually in the second case, we use this technique. So we split the time into the multiple of period t, and so we repeat this procedure.
I see. Thank you.
Hi, thanks for the nice talk. A question on this cutoff you're doing. Doesn't this mean that, in the end, the Hamiltonian you're simulating is not continuously depending on t anymore? So what you're actually doing is simulating like just a bunch of time-independent Hamiltonians?
So
like a finite series of them?
Actually, so I couldn't catch what you mean. So sorry. Actually, so time periodicity is completely designated by this cutoff here. So if we use this.
No, sorry, I mean the cutoff of the. You Fourier transform from basically from the unit circle to the integers, and then you cut off the integers, which means that basically your Fourier transform is between some c to the d to some other c to the d, depending on what you cut off. So
maybe that's right. So, so how to say? Sorry. Maybe as you can. However, so actually maybe this form is quite so. So for example, so I also derived our algorithm for multi-periodic time-dependent systems. In that case, so this is not a so simple form. So which maps so Gn to Z. So in that case, maybe I think the significant element for our algorithm is so this is given by so the derivative of the time periodic Hamiltonian is in a given certain form, right? Sorry.
Okay, thanks.
Thanks for the talk. So recently there's another work by Nathan Wabe with the time-dependent Hamiltonian simulation with discrete clock constructions. I'm not sure if you're familiar with that. It seems in their work they also achieved this additive query complexity with some special models. I'm not sure how to compare with the.
Sorry, I do not know the detail of this work, but actually, I think that that work requires so the derivative of the Hamiltonian should be vanished, right? So the two derivatives, right? Maybe in that case, in our cases, so the second derivative of the Hamiltonian does not vanish, and in that case, our algorithm can overwhelm that one, right? Yeah.
Okay, thanks.
Thanks, sir.
Thanks for the nice talk.
Yeah.
And my question is, what is your order of the capital T? Is it a constant?
Yeah.
And does the algorithm works for a larger T, larger capital T, say, probably in system size or exponentially in system size? Does it still work?
Actually, the capital T is here, so we assume that frequency is size independent. So capital T can be large infinitely. So can be maybe yeah. Sorry.
I mean, if T is say a polynomial function in the system size.
Yeah, actually, so T can be arbitrarily large in our algorithm. In that case, so our algorithm, so the time scale belongs to the first case, and the correct complexity completely corresponds to the qubitization technique.
Oh, okay.
Yeah.
Oh, thank you.
Yeah.
Any other questions? If not, let's thank the speaker again.